Welcome. We are continuing on in Chapter 4, the applications of the derivative, and today we look at 4.6, the mean value theorem. And what we have here is the big idea. There is an x value whose instantaneous rate of change is the same as the average rate of change, and we'll explore what that means. It begins with Rolle's theorem. Here's a basic theorem, and then we will generalize this to get the mean value theorem. Okay, so let's think carefully about what's going on. Let f be a differentiable function. So differentiable means nice and smooth. It's defined on the closed interval from a to b. So it's defined at a, it's defined at b, and it's defined everywhere in between. And suppose that f of a equals f of b. So the y value at a is the same as the y value at b. So your function might look something like this. Maybe it comes up through a, it's nice and smooth, no sudden twists or turns. And there we go. It is a nice differentiable function defined entirely throughout that interval, and f of a equals f of b. That's the setup. If that's the case, Rolle's theorem says if f is differentiable on the closed interval from a to b, and if f of a equals f of b, then there is some point c in the interval, open interval from a to b, such that f has a horizontal tangent line at x equals c. So what does that mean? So there's some point c strictly in between a and b where f has a horizontal tangent line at that c. And so that actually happens right here. You can see there's a horizontal tangent line right at the top of the hill. And so that might be one of my c values. Now, one of my c values. It just says that there is some point c. There might be several points. So in fact, in the picture I drew, there are in fact 2 points. So there's another horizontal tangent right about there. And so maybe that's another value that we would call c. So maybe we could call this c1 and c2. That's Rolle's theorem. It just shows the existence of horizontal tangents. And the key values, two hypotheses, f has to be differentiable, and the height at a is the same as the height at b. F of a equals f of b. The mean value theorem generalizes Rolle's theorem a little bit. It doesn't require that f of a equals f of b. In the picture here, you can see that f of a and f of b are two different values. So let's take a look at the mean value theorem. It says, if f is differentiable on the closed interval from a to b, then there exists a value c between a and b such that, well, what's going on here? So this is my c, and what is the slope of that line? Well, it's the same as the slope of the line connecting the point a f of a and b f of b. So let's see here. That slope is change in y over change in x, f of b minus f of a all over b minus a. But the other line I have, that's just a tangent line. That's f prime at c. That's the slope of that line. So it's saying that the f prime of c actually is f of b minus f of a over b minus a. And this is where the name mean value theorem comes in. Mean means average. And the expression for the slope between the 2 points, this f of b minus f of a over b minus a, that's the average rate of change from a to b. That's the, so to speak, it's the average slope of the function from a to b. And so it says that the instantaneous rate of change at c is equal to the average rate of change, or the mean rate of change from a to b. All right, so again, watching our hypotheses, f is differentiable, then there's a point c in between where the instantaneous rate at c equals the average rate of change from a to b. Let's look at a demonstration of the mean value theorem in action. Okay, so in this demonstration, we have a function there. You can see it's listed. That's f of x. And if I connect 2 points, we get that. And I can choose my a and my b. I can move the point on the right, and you can see that changes the value of b. b is the x value of that point. And if I change the point on the left, then the x value of that point is a. And so, given this function, I have two different values. I have an a and a b. The mean value theorem says that there are some points between a and b. There are some x values between a and b where the slope of the curve will be the same. And let's take a look. Here it is. So you can see there are three different values, three different c values, and there they are. They're listed, negative 2.39, 0.34, 2.05, and that's where the slope of the tangent is the same as the slope of the secant line. The instantaneous rate of change is the same as the average rate of change. And so it's actually kind of fun to play around with this thing, move it around a little bit. You can see how things change. Here we go. At this point, there's only two values of c that work. If I come in between, now there's only one c that works. Here's another example. So just a parabola opening downwards. As I change my a and b, there's always some c in between them where the slope of the tangent is the same as the slope of the secant. The instantaneous rate of change is the same as the average rate of change. Here's another example. So you can have lots and lots of those points C. This emphasizes the hypotheses. This function looks nice and smooth, but it's discontinuous, right? So it's discontinuous at 0. It's not differentiable all the way from a to b. Consequently, I don't see a point in between a and b where the slope of the tangent is the same as the slope of the secant. Now, I can make it so. I think maybe if I pull this out far enough, it might be the case that there's a c value in between those two things where the slope of the tangent is the same as the slope of the secant, but it's just not that it's guaranteed to exist. It doesn't have to be there. The mean value theorem says that if my function is continuous and differentiable between those 2 points, then the existence of c is guaranteed. Here's one more example. In this case, the function is even continuous, but it just has one x value where it's not differentiable, right at 0. See, the function is the absolute value of x minus 0.1 x squared. And so, yeah, there's no c value where the slope at c is the same as the slope of the average rate of change. Of course, I can make it appear. It might appear, but it doesn't necessarily have to. All right, let's go back to the slides. Here's an example with some calculation. Let f of x equal x to the 4. What is the slope of the line connecting 0, 0 and 2, 16? So my a is going to be the 0, the x value there, and b is the 2. Right? So change in y over change in x, so 16 minus 0 over 2 minus 0 equals 8. So the slope of that line is 8. By the mean value theorem, there's some c somewhere in between 0 and 2, such that f prime of c equals 8. Can I find that number? And just eyeballing it, right? Kind of, I make a parallel line, looks something like that. All right, so I'm expecting that this value of c is somewhere in between 1 and 2. Let's actually find it. Okay, so I'll differentiate my function. F of x equals x to the 4. So f prime of x equals 4x cubed. Now, I'm guaranteed that there is some c, so that f prime of c equals 8. So f prime of c equals 4c cubed equals 8. And now let's solve 4c cubed equals 8. We'll solve that for c and find out what we get. So c cubed equals 2. Take the cube root. C equals the cube root of 2. And that's our answer. My c value is the cube root of 2. This kind of a problem is like what you'll see on the homework, some computations where they say, here's the function, here's an a and the b, and find that c in between that gives you f prime of c equals the average rate of change. Now, there are two really neat consequences of the mean value theorem, and they really kind of show us how derivatives work deep down inside, and these will be very useful to us in the second part of the course where we really get into integration. The first consequence is that zero derivative implies a constant function. Now, let's take that the other way around. If I have a constant function, say f of x equals 10, we know that the derivative of a constant is 0. F prime of x equals 0. And that's true for any constant that I pick. If my f of x was pi, f prime of x is 0. If f of x is negative 17.3, f prime of x is 0. So given any constant, the derivative is 0. But there's a question you might have. Could there be some function that's not constant where the derivative of that thing still equals 0? Could there be some non-constant function whose derivative is 0? And this consequence answers that question. It says, no. Zero derivative implies constant function. The only way that I can have my derivative being 0 is if this original function that I started off with is a constant. Okay, so let's see why that is true. And we'll go through the proof. So let's suppose that I have a function f, and truly f prime of x equals 0. Well, and we'll say for all x. My goal is to prove that f of x, the original function f, actually equals some constant. We'll call it c. So let a and b be arbitrary x values with a less than b. Let me draw a little picture here. So I have my axes, and here's some value a and some value b. And by the mean value theorem, are my hypotheses satisfied for the mean value theorem? This function is differentiable all throughout a and b, so that's good. That's all I really need. By the mean value theorem, there is some value c strictly in between a and b, so that f of b minus f of a divided by b minus a equals f prime of c. Anyway, that is the mean value theorem. Well, what's f prime of c? Of course, f prime of c is 0 because f prime of x equals 0 for all x. So this guy on the right, that actually equals 0. So my fraction, f of b minus f of a over b minus a, that whole thing equals 0 too, right? And so by multiplying both sides by that denominator, b minus a, I can clear out that denominator and I find that f of b minus f of a equals 0. Now, add f of a to both sides, I get f of b equals f of a. Oh, okay, so let me add to the graph a little bit. However high the graph is above a, it's also that high above b. In fact, let's go ahead and give that a name. That height, we'll call it capital C. Since a and b were chosen arbitrarily, f of x has the same value for all x. And this is kind of the big jump in the proof. A and b were chosen arbitrarily. So look at the picture. I'll erase b. Maybe that wasn't really the b I intended. Maybe I intended b over there. Well, I would have found that f of b is the same as f of a. Oh, but maybe I meant for my b to be over there. Well, it's the same thing. F of b would have to be equal f of a. No matter where the b is chosen arbitrarily. It has to be the same value at f of a. And so that has to be that same value c. And what do I find? That the function is actually constant for any x value that I plug in. So in other words, that is f of x equals c for some real number c. And that's it. We've shown that f is a constant. There it is, by the power of the mean value theorem. There's a second consequence, which is really an immediate consequence of the first one. Functions with equal derivatives differ by a constant. So in other words, for example, if f prime of x equals g prime of x, so these two functions have the same derivative, then really f of x equals g of x plus c. Now, do you remember what adding a constant to a function does. That just lifts it up or down a little bit. So if my f looks like that, then my g function will just be basically the same thing, kind of lifted up a little bit or down. But in order for two functions to have the same derivative, they have to look like each other, just shifted up or down. At this point, pause the video, see if you can fill in those blanks and complete the proof. Then, when you're ready, start it up again, and I will fill it in. All right, give it a try. So, let's take a look here. How do we finish this? Let f of x and g of x be a pair of functions such that f prime of x equals g prime of x for all x. Let h of x be the difference. Then h prime of x is f prime of x minus g prime of x. And that equals 0 because f prime of x equals g prime of x. By applying the previous theorem, that is, by applying the consequence 1, we see that h of x equals c for some number c. That is, f of x minus g of x equals c. In other words, f of x equals g of x plus c. All right, and that is it for the mean value theorem. It's kind of an interesting theorem that shows us how derivatives work, some of the power of derivatives, but more importantly, is actually this consequence 1 and 2. Down the road, these end up being some really useful tools for us. All right, and that's it.